All right, Chemistry 111. This is just Chapter 9, which deals with chemical bonding, basic concepts of chemical bonding. Namely, we're going to spend a lot of time talking about ionic bonding and covalent bonding. Those will be the two major focuses of this chapter. But before we can get into actually putting atoms together in a bond, we have to get back to valence electrons and discuss a little bit more about valence electrons. And we spent some time talking about valence electrons when we looked at electron configuration, and we said, okay, well, we've got the electrons with the highest principal quantum number. These are going to be outer electrons or valence electrons. Well, this evening, we're mostly going to focus on the valence electrons of the representative elements. So these would be elements that are found in groups 1A through 7A. Let's take a look at the definition of valence electrons. Valence electrons are outer shell electrons of an atom. The valence electrons are the electrons that participate in chemical bonding. And since the whole point of this chapter is to cover chemical bonding, before we can get into really what chemical bonding is, before we can start talking about ionic bonds and covalent bonds, we have to understand valence electrons. Now, atoms are always going to combine in order to achieve a more stable electron configuration. If you remember, when we talked about the charges of cations and anions, we said, well, a group 1A metal is going to form a +1 ion, a group 2A is going to form a +2 ion, a group 3A is going to form, usually a +3 cation. So we talked about how metals like to lose electrons. And the reason why is because they kind of have an identity crisis, right? They want to lose as many electrons as it takes for them to become isoelectronic with a noble gas. When we get over into the nonmetals, over here, we see that these elements tend to gain electrons, don't they? They tend to form anions, and they want to gain as many electrons as is necessary in order to become isoelectronic with a noble gas. And something else that you notice here is that all of the elements in group 1A have one valence electron, right? They have the same outer electron configuration, right? That S1. So they all have one valence electron. Same thing with group 2A, 3A, 4A, 5A, 6A, and 7A. And of course, if you go to group 8A, you'll see that the noble gases have 8 valence electrons. And so again, I just want to remind you that maximum stability is going to result when an atom is isoelectronic with a noble gas. So that's a theme that's going to come up over and over throughout the course of this lecture. Well, let's move on to the next slide and talk about what are called Lewis dot symbols for the representative elements and noble gases. Remember again that the representative elements, these are the elements that are found in groups 1A to 7A, and the noble gases, these are, as you know, the elements that are found in group 8A. Now you notice we have all the representative elements on here, and we have the noble gases on here, and they're surrounded by some dots. So what do these dots represent? Well, you can probably connect the dots, no pun intended, that the number of dots that are surrounding each one of these atoms is the same as the group number, right? If we were to take a look at it, for example, at nitrogen. Nitrogen is in group 5A. You can see that it is surrounded by 5 dots. If you tried, looking at sulfur, you can see it's surrounded by 6 dots. It's in group 6A. So these Lewis dot symbols simply represent the number of valence electrons around each element. Now, we use these as a way to keep track of valence electrons. Now, something that you notice here is that the transition metals, we don't have any Lewis dot symbols for those, and that's because they all have incompletely filled inner shells, so we're not going to write Lewis symbols for them or for the lanthanides and actinides. So again, we're going to focus on the representative elements this evening. But what am I getting at here is that each one of these Lewis dot symbols that we see here represents the element as well as the number of electrons surrounding that element. So a couple of just nuances I want to let you know before we move on, because it looks really simple. You say, okay, I've got carbon, it's in group 4A, it's surrounded by 4 electrons. So something that you need to know is that when you're drawing a Lewis dot symbol, you draw the elemental symbol. Now you know it's in group 4A, carbon. It's going to be surrounded by 4 electrons. So we always have the maximum number of unpaired electrons. So the carbon atom has 4 sides around it, right? Every one of the elements, the letters, we say it's got 4 sides around it, and we are going to place 1, 2, 3, 4 electrons around it like this. So the maximum number of unpaired electrons. So what I'm saying is if you were to say 1, 2, 3, 4 like this, that would be incorrect. That's an incorrect Lewis dot symbol. Now, once we get to an element like nitrogen, okay, if we get to nitrogen, well, then we've got 5. So then we would go 1, 2, 3, 4, 5 like this. Some other nuances that students have asked me about in the past, the students can sometimes really get into splitting hairs. And I know what you're thinking, well, instructors can too. Yeah. Well, let's say you had nitrogen. Again, it wouldn't matter if you had the pair of electrons on this side. It doesn't really matter. Okay, that's not important. If you were to put the pair of electrons over here like that, as long as you have the maximum number of unpaired electrons. So just give me a thumbs up in the chat if you just follow me on the concept of Lewis dot symbols. We're going to see how to use these Lewis dot symbols to assemble structures later on. Okay, cool. Great. Yeah, it's not meant to be really a mind-boggling concept or something, but it's a very important fundamental concept that you get down before we move on into looking at ionic bonds and into covalent bonds. There we go. So Lewis dot symbols. All right, there we go. And we're going to use these a lot this evening. So let's move on from there and let's talk about what an ionic bond is, right? We've talked about ionic compounds when we looked at nomenclature, and we said, okay, well, an ionic compound is usually formed between the cation of a metal and the anion of a nonmetal. An ionic bond can be defined, as I have here, as an electrostatic force that holds ions together in an ionic compound. What is that electrostatic force, right? We have a positive charge and a negative charge, right? And they're going to be attracted to one another. Opposites attract. So let's say we're making the compound lithium fluoride. Okay, so here's some lithium fluoride right here. You can see it's just a white solid. It's poisonous. Anyhow, but if we look at the electron configuration for lithium, 1s2, 2s1, you see that lithium has one valence electron. So that's why we have one dot, right? One unpaired electron around our lithium. If we look at fluorine and we look at its electron configuration, it's 1s2, 2s2, 2p5. Just like the lithium that had one valence electron, the 2s and 2p are my valence electrons. I have a total of 2 plus 5, which is 7. Now, again, you knew that because lithium is in group 1a and fluorine is in group 7a. So again, the fluorine is surrounded by 7 electrons. So what happens when the fluorine and the lithium come together? Well, we know that lithium has a tendency to lose electrons because it's a metal. We looked at ionization energies earlier on. We know that fluorine has a high electron affinity. It has a desire to take on an electron. And so essentially the lithium gives up its electron to the fluorine. Now look at what happens. We make this ionic compound, lithium fluoride, and if you look at the electron configurations of the cation and the anion, you see that they're both isoelectronic with the noble gas. It's like, haha, we did it, right? Again, the elements have that identity crisis, if you will. They want to become isoelectronic with the noble gas, and you can see that we got that to happen when the lithium lost an electron. Now it's isoelectronic with helium, and when the fluorine gained an electron to form fluoride, it became isoelectronic with neon. So everybody's happy. Now, what if you were to think about this process of forming lithium fluoride? What if you were to think about it in terms of steps, right? In a stepwise. Well, because what if you think about step 1 as being, well, lithium has to lose an electron, doesn't it? It has to give up that electron. Okay, well, if lithium gives up an electron, it's going to form a lithium cation, plus we're going to have an electron left over. Well, what if the fluorine accepts that electron in the second step? Okay, now what have we got? And this should have a negative charge. Well, that's a typo there. There should be a fluoride here. Anyhow, I digress. So now we've got the fluoride and we've got the lithium cation. And now the fluoride and the lithium cation, we have a positive and a negative charge. What's an ionic bond? It's an electrostatic force between a positive and a negative charge, a cation and an anion. So those are going to come together to form our ionic compound. If you tally up these 3 reactions, these 3 steps that I have over here, the electrons are going to cancel, the lithium cation is going to cancel, the fluoride anion is going to cancel, and what are we left over with at the end? We're left over with the lithium with our unpaired electron plus the fluorine with 7 valence electrons forming lithium, forming lithium fluoride. There we go. Look familiar? Because this is the exact same thing that we have right here. So we can even think of this as being the sum of these three equations. Again, the ionic bond is the result of that positive and negative attraction, right, between the positively charged cation and the negatively charged anion. And so that, in a nutshell, is what an ionic bond is. Well, with that in mind, let's try a practice problem. This is example 9.1 from our book. It says you use Lewis dot symbols to show the formation of aluminum oxide. So aluminum oxide is found in things like rubies and sapphires. Anyhow, they're varieties of corundum. Anyhow, I'm not an expert in minerals, but anyhow, I'm not a mega fan of this question. I don't think there's anything wrong with it, but I don't think I would ask exactly this type of question on an exam. But the concept is a very good one, that you have to be sure that you understand the concept of what's going on here. Well, the formula of our aluminum oxide is Al2O3. So there's the formula of our aluminum oxide. Now, in aluminum oxide, we've got 2 aluminum atoms and we've got 3 oxygen atoms. So if we write out the Lewis dot symbol for 2 aluminum atoms, so we have an aluminum. Aluminum is in group 3A, so it's going to be surrounded by 3 valence electrons, and we've got 2 aluminums. Now let's write down what the electron configuration for aluminum is. The noble gas that precedes aluminum is neon, so I'll put that in my square brackets. And again, we went over this in the electron configuration portion of the class. So we have neon, then we have 3s2, 3p1. There we go. So that represents our valence electrons for our neon. Then we're going to combine that with the 3 oxygens. Oxygen comes from group 6A, so it's got 6 valence electrons. So I have 3 oxygens, and oxygens has 1, 2, 3, 4, 5, 6. Its electron configuration is 1s2, 2s2, 2p4. All right. So what's going to happen is that the aluminum, being the metal, is going to lose all of those electrons, and the oxygen is going to gain them. So what's that going to look like? We're going to end up with 2 aluminum 3+ cations, right? If it loses the 1, 2, 3 electrons, it's going to have a triple positive charge, or 3+ charge. So we've got our 2 aluminum 3+ ions. Now 2 times 3 is 6. If I have room for 2 more electrons, right? I've only got 6 electrons surrounding my oxygen, and I've got 3 oxygens. So 2 times 3 is 6, right? So all 3 of those oxygens are going to take my 6 electrons from my aluminum, and I'm going to end up with, 3 oxides, right? And if I put all the valence electrons around oxide, it's going to have 8 valence electrons. And so the aluminum is now isoelectronic with neon, right? If you look at your periodic table, aluminum, look, we go back here, we see aluminum, we go back 1, 2, 3, right? 13 subtract 3 gives you 10, isoelectronic with neon, so that looks good. And our oxygen gains 1, 2 electrons to become isoelectronic with neon, and that's why it forms oxide, or O2-. So there we go. So both of these are isoelectronic with neon like that. Again, everybody's happy, right? The elements are both now isoelectronic with a noble gas. And now we have the aluminum 3+ ion. We've got 2 of them that are going to combine with the 3 oxide ions to form our aluminum oxide. And there we go. We used our Lewis dot symbols to show how aluminum is going to lose its valence electrons. The oxygens are going to gain the valence electrons, and we end up with a neutral compound, which is the aluminum oxide. So we can even add to this and just say we have the 2 aluminums and the 3 oxygens, which are going to form Al2O3, which is a solid, of course. And there you have it like that. Give me a thumbs up if you follow me on the whole concept of just the metal losing valence electrons, the non-metal gaining valence electrons. Okay, very important concept. Okay, very important concept, ionic bonding. All right, and again, we looked at ionic bonding to some degree when we discussed nomenclature earlier on in the class. Well, how do we quantify the strength of an ionic bond? How strong is an ionic bond? You're thinking, well, I got positive and negative charges that are, attracting each other. And the way that we quantify the strength of an ionic bond is using what's called lattice energy. So lattice energy is the energy that's required to completely separate 1 mole of a solid ionic compound into gaseous ions. Now the example I'm going to use is, let's say we had lithium fluoride. Okay, so if we had lithium fluoride, it's an ionic compound, it's a solid. Now if we had 1 mole of solid lithium fluoride and we could somehow separate it into completely into its ions in the gaseous phase, right? Gaseous ions. So in the gaseous phase, okay, the amount of energy that it would take to do that, we would call that the lattice energy. So we call that delta H of our lattice, right? And that's going to be a positive quantity, isn't it, right? It's going to take a lot of energy to pull apart all these ions that have the strong electrostatic force and to separate them into the gas phase. All right. Well, luckily, we know that our lattice energy is related to Coulomb's law, which I have here. And you don't have to be an expert in Coulomb's law. All I want you to understand is that our lattice energy, E, and I'm going to rewrite this equation, just say E is directly proportional to the product of the charges of the cation and the anion divided by the distance between the ions. So what does that mean? What that means is that the higher the charge of my ions, the lattice energy is going to be a bigger number. It's going to increase. It's going to go up. And as the R, or the distance between the ions, gets smaller, my lattice energy is also going to go up. So again, you just have to know that the lattice energy, E, is directly proportional to the product of the charges of the cation and anion, and it's inversely proportional to the distance between the ions. So with all that in mind, if you're like, what does that mean exactly? What are you talking about? Product of charges, what does that exactly mean? Well, let's take a look. If we look at some examples that are shown here, and we know our formula, which is the lattice energy is directly proportional to the product of the charge of the cation and the anion divided by the distance between the ions. Well, let's compare magnesium fluoride and magnesium oxide. We know that magnesium is a group 2A element, so the charge on magnesium is going to be +2 no matter what. But we know the charge on fluoride, which is a halogen, is in group 7A. It's going to be -1. Right? The charge on oxygen, when it forms an oxide, is going to be -2. Now, if you have +2 times -1, you get -2. And so that is a smaller number than if you take +2 times -2, you get -4, right? So you can see how or why magnesium oxide would have a stronger or a greater lattice energy, right? Because the product of the charges of the cation and the anion are going to be greater. Now, let me just address the fact that the E value that you would get here would be negative, right? Because you're like, well, I thought you just said it would be a positive quantity, lattice energy. Well, the energy here, we're talking about the energy that would be released when that cation and the anion come together. So it gives you a negative value. But again, lattice energy is going to be a positive value because you have to put in energy to pull those ions apart. Now, if we look at this example over here, we have lithium fluoride and lithium chloride, right? It doesn't matter. The lithiums are always +1. Fluoride and chloride are both halogens. They're going to be -1. And so we can't use the product of Q for the cation and the anion to rationalize the difference in lattice energy. But we see that fluorine, the lithium fluoride, has a higher lattice energy. What is that based off of? It's going to be based off of R, right? The distance between the ions, because we know that when we go down the halogens from fluorine to chlorine to bromine to iodine, that fluorine is smaller. And we know that as R decreases, right, as the denominator gets smaller, our lattice energy is going to be greater, right? So the radius of a fluoride is smaller than the radius of a chloride. So that's the whole rationale there. Well, let's talk about how we would quantify lattice energy. And if you got my email today that I sent you, I put in a link to a very short video, a very short YouTube video about the Born-Haber cycle and how it's used to determine lattice energy. What's interesting is if you look at the overall heat of formation of lithium fluoride, you can see that it's this big negative value of negative 594.1 kilojoules. So a lot of heat is given off when we form lithium fluoride. But if you look at the formation of ions from solid lithium and from fluorine in the gaseous phase, if you just take a quick peek at what it takes to make those ions, you might not, you might be prone to say, well, that doesn't make sense. Like, how would I end up with so much heat given off when I combine lithium and fluorine to make solid lithium fluoride? Well, I want to walk you through what's called the Born-Haber cycle, which is going to explain why the heat of formation of lithium fluoride, why it's so negative, why it's so exothermic. And we're in the process, we're going to see how to calculate lattice energy, because lattice energy cannot be calculated directly. But luckily, thanks to the Born-Haber cycle, we're able to find a workaround. So see if you can follow along with me here. And I'm going to try to keep this as brief as possible. But if we're starting out with just by taking the heat of formation into account, I just want to have this on the slide for you to look at. We said we take lithium and we need to combine that with half a mole of fluorine in the gaseous phase. Remember, fluorine is a diatomic element. We're going to need half a mole because we only need one fluorine atom, okay, or 1 mole of fluorine to form lithium fluoride in the solid phase. And we said the heat of formation of this reaction is negative 594.1 kilojoules per mole. So I want you to keep that in mind while we work and try to determine lattice energy. And let me show you how we do that. So first of all, if we're just starting it with solid lithium, I mean, how are we going to get that to be converted into a lithium ion is what I was trying to say. We want it to convert it into a lithium ion in the gaseous phase. So the first thing we're going to do is we're going to convert it into a gas, to lithium gas, and that process is called sublimation. And you can imagine that this is an endothermic process. We have to put energy in to convert the solid into a gas, and that costs 155.2 kilojoules per mole. Similarly, if we start it with half a mole of fluorine in the gaseous phase, but we only need one fluorine, what we have to do is break the bond in the fluorine molecule because it's F2, right? Fluorine comes in packets of 2. And so we have to break that apart. And we call that the bond enthalpy. And we're going to talk more about bond enthalpies later on. But for now, it's just the amount of energy that it requires to break the 2 fluorine atoms apart, okay? And we need half the amount of energy that it takes to break apart 1 mole of fluorine. And I've already gone ahead and done the math on that. And it's 75.3 kilojoules per mole to do that. But now all we have are atoms in the gaseous phase. We don't have ions yet, do we? Well, if we take our lithium in the gaseous phase and we look at its ionization energy to convert it into a lithium ion where it's lost an electron, we call this the ionization energy. And again, we discussed that earlier on in the thermochemistry chapter. We have 520 kilojoules per mole. Look at everything that we've done so far. You know, look at all these. Everything's a positive value. It kind of makes you wonder, like, where is this negative value going to come from? Well, hold on. We're going to look at the electron affinity for our fluorine. If it gains an electron to form the fluoride ion, right? Because we need a fluoride ion in the gaseous phase. I don't know why I called it a cation when it's an anion. And yeah, there we go. And the electron affinity for my fluorine is equal to negative 328 kilojoules per mole. Well, now, if I combine my lithium ion in the gaseous phase plus my fluoride ion in the gaseous phase to form lithium fluoride in the solid phase, this is the delta H, and this is the negative of the lattice energy. Lattice energy. Don't believe me? Well, if we go back here, I said, what was lattice energy earlier on? I said lattice energy was the exact opposite of that. I said it was taking the 1 mole of the solid and converting it into gaseous ions. That was lattice energy. Look carefully at this equation that I just highlighted, or this reaction that I just highlighted. what I have here is the exact opposite. So if we can figure out what this number is, then we've got the negative of the lattice energy. Just for interest sake, I'm just going to call this X to make it nice and simple. Now look what happens when we tally all this up. Okay, when we add all this up together, we end up canceling our lithium in the gaseous phase. We cancel our fluorine in the gaseous phase. We can cancel our electrons like that. We can cancel our lithium ions, and we can cancel our fluoride ions. Now what are we left over with? We're left over with solid lithium plus half a mole of fluorine to give us lithium fluoride. Let's write that down. I'm going to use green pen here. So I have solid lithium plus half a mole of fluorine in the gaseous phase produces lithium fluoride solid. Look familiar? It's this reaction that I had up here. Okay, and we know the delta H of that reaction. The delta H of formation of lithium fluoride is equal to negative 594.1 0.1 kilojoules per mole, like that. Now, keeping in mind that the sum of all these enthalpy changes for the steps that we've got written out here is equal to the enthalpy change for the overall reaction, now all we can do, or now all we've got to do, is solve for X. Now, if you're wondering, what do you mean exactly by that? Well, look, I got some more room over here, and what I mean is this. The delta H of formation for our lithium fluoride is going to be equal to the delta H of the sublimation of the lithium plus the delta H of the bond energy or bond enthalpy of the fluorine gas plus the delta H of the ionization energy plus for the lithium plus the delta H of the electron affinity of the fluorine plus X, which is the negative of my lattice energy. Okay, I've got all of these values except for X. So now I can solve for X, and I can say X is going to be equal to the delta H of formation of my lithium fluoride, subtract the delta H of sublimation plus the delta H of the bond enthalpy plus the delta H of the ionization energy plus the delta H of my electron affinity. There we go. And we have all of these numbers. So really all we have to do is plug them in. I'll show you quickly, and you can double check my math on this. We have negative 594.1, subtract 155.2 plus 75.3 plus 520 plus, or sorry, subtract 328, like that, and all of that is kilojoules per mole. And when we do that, we get that our X is equal to negative 1,017 kilojoules per mole. This means that our lattice energy is going to be the opposite sign, right? It's going to be equal to positive 1,017 kilojoules per mole. So this is the Born-Haber cycle, and this is how we measure the lattice energy of an ionic compound. Right? We can't measure it directly, but we can use, again, the fact that the sum of the enthalpy changes for the steps is equal to the enthalpy change for the overall reaction, and all we have to do is solve for that missing step, which was our lattice energy. So all we did was use these values and this value, and we used it to solve for our lattice energy. So that, in a nutshell, is the Born-Haber cycle. I remember the first time I heard about the Born-Haber cycle in my first year of college, and thinking, wow, that's really complicated. But after I tried a couple of practice problems, I was like, oh, I get it. You know, it's not that bad. So I encourage you to try some of the practice problems that I've selected from the textbook that deal with lattice energy. Now, a little more about lattice energy, right? Because lattice energy is a value. It's something, you know, that we can quantify. And if you look at this table here, which shows lattice energies and melting points of some ionic compounds, you'll see that there's a rough correlation between lattice energy and melting point. Just for example, if we look at these ionic compounds where lithium is the cation, I don't know what Lil is, that's supposed to be lithium iodide. But anyhow, you see that as the lattice energy goes up, right, the compound, the electrostatic forces are going to be stronger and stronger, and therefore it's going to take more and more heat to take that solid, those solid ionic compounds, and convert them into the liquid phase to melt an ionic compound, right? To have a molten ionic compound. Something else that's kind of interesting down here is just, staying with the whole, concept of Coulomb's law. Again, you see here with magnesium oxide that the lattice energy is higher than everything else that's on here. And it's because both the anion and the cation have a 2 charge, right? Magnesium being +2 and oxide being -2. Anyhow, there we go. So that covers the Born-Haber cycle and how we use the Born-Haber cycle. So again, ionic bonds, metals and nonmetals most of the time. The metals want to lose electrons to become isoelectronic with a noble gas. Nonmetals want to gain electrons to become isoelectronic with a noble gas. And then we form an ionic compound, which is the result of an electrostatic interaction between the anion and the cation. What else do you have to know? You have to understand the concept of lattice energy. I want you to know this definition that I have back here for lattice energy. So you should have that memorized, that it's the amount of energy required to completely separate 1 mole of solid ionic compound into gaseous ions. And that's going to be a positive value, right? Think about it. If you have a sodium chloride crystal and you had to tear apart all those little ions in there into the gaseous phase, that would take energy in order to do that. The last thing you need to know about this section on ionic bonding is the Born-Haber cycle and how we can use the Born-Haber cycle to calculate lattice energy. All right, well, from there, we're going to move on to something a little bit different. We're still in the vein of bonding, again, because that's the subject of this chapter, but now we're going to move on to covalent bonds. We're going to spend a lot more time, or I'd say a significant amount of time talking about covalent bonds. Covalent bonds are really important, and covalent bonds will also be discussed a lot in chapter 10, where we talk about molecular geometry and the concept of what is called hybridization, which we haven't even touched on yet. Anyhow, a covalent bond, unlike an ionic bond, is a chemical bond in which 2 or more electrons are shared by 2 atoms. So we have a bond, and in that bond, we have 2 electrons that are shared. Now, I'm not really good at doing animation on my iPad, but let's say we have 2 hydrogen atoms, okay? We have 2 hydrogen atoms that each have 1 unpaired electron, so this is their Lewis dot symbol. Now, if these 2 hydrogen atoms, get closer and closer together, as these get closer and closer together, what happens is that there's attraction between the electrons and the nuclei. Okay, so this electron, I'll highlight it in red, maybe, is going to be attracted to the nucleus of this hydrogen atom. And what happens is they come together and they share those 2 electrons so that they both have a noble gas configuration. Now, for hydrogen, the noble gas configuration would be helium, so they only need 2 electrons, but they're going to share those 2 electrons in that bond. And the distance between the 2 hydrogen atoms at this point where they're sharing those 2 electrons, this is where the attractive forces are maximized and the repulsive forces between the 2 nuclei and the electrons are minimized. So attractive forces maximized, repulsive forces minimized. So every time you see me draw a line between 2 atoms, you know that there are 2 electrons inside that line. There are 2 electrons being shared there. Now, a little bit more about this noble gas configuration thing. Now, what is sharing? If you're sharing something with somebody else, it means you both have the benefit of it, right? You're both able to use it. And so since this hydrogen that I'm circling in blue right now is sharing the 2 electrons in that bond, it's as if it's got the 2 electrons, and it's as if its electron configuration would be 1s2, which is the electron configuration of helium, which is a noble gas. The same thing also applies to this hydrogen atom, though, right? It also has the benefit of those 2 electrons in that bond that are being shared. And so it's like it also has the electron configuration of a noble gas. Give me a thumbs up if you follow me on that idea. I'm going to go over it again with the fluorine atom, but I just want to see, is anybody with me on this? The concept of atoms coming together, sharing electrons. Anybody besides Branson? I'm happy you're following me, Branson. That's good. All right. All right. Anyhow, let's move on. Again, stop me if you have any questions. So again, if you're not following me 100%, let's address this question that I have outlined on my slide here. Why should two atoms share electrons? Let's take a look at fluorine. You memorized the diatomic elements earlier on in the class, right? We have, the mnemonic Brinkelhoff that you can use to memorize the diatomic elements, but you know that fluorine is found in packets of 2, is F2. Well, if we look at the number of valence electrons of fluorine, right? Fluorine is in group 7A. It's got 7 valence electrons. What happens when 2 fluorines come together, right? Now, when the 2 fluorines come together, right, they share these 2 electrons, right? They share the 2 electrons that are kind of in this portion right here, this part of this, what looks like a Venn diagram, okay? This comes from our textbook, okay? And so the way that we would represent that, okay, the valence electrons, is we would just represent it like this. I'll just draw it out for you. We would draw the fluorines connected by a bond like this, and then any electron that's not participating in bonding, we would draw surrounding the fluorines. And so we call those electrons lone pairs. So my lone pairs would be, here's my yellow pen, would be, this is a lone pair, this is a lone pair, this is. So those are my lone pairs, and the 2 shared electrons are in my single covalent bond. Now, if we tally up the total number of electrons that each fluorine has the benefit of, and I'm not going to write this down, but the electron configuration of fluorine is 1s2, 2s2, 2p5. But now, since they both got that extra electron, they both have the electron configuration of neon, right? They both have that 1s2, 2s2, 2p6. There we go. So that's why they're going to come together to share electrons. Now, if you've studied chemistry in high school, you might have heard of the octet rule, which is that any atom, or an atom, I should say, other than hydrogen tends to form bonds until it's surrounded by 8 electrons. So that's the octet rule. And if you look at the 2 fluorines in our F2 molecule, and I'll just erase this stuff here just for a second, okay? The octet rule said that an atom other than hydrogen tends to form bonds until it's surrounded by 8 electrons. Let's take a look. Let's just examine this fluorine here. How many electrons is it surrounded by? 1, 2, 3, 4, 5, 6, 7, 8, right? Because it has the benefit of both of the electrons in this single bond. This fluorine, 1, 2, 3, 4, 5, 6, 7, 8. And that's something that we're going to see over and over and over throughout this class and throughout this chapter. All right. And again, you have to be solid on the concepts of covalent bonding in order to master the content, not only in chapter 9, but in chapter 10 as well. Well, with that in mind, I want to just take a moment here and talk about a water molecule, okay? H2O, molecule that everybody's familiar with. Sometimes you even see H2O written in commercials, written like this, and it has this kind of angle in it. And there's a good reason why H2O is drawn with an angle, but that's not really the focus of our conversation tonight. Well, how many valence electrons does hydrogen have? Can anybody tell me? And it's not a trick question. One hydrogen atom. How many valence electrons does one hydrogen atom have? Yeah, exactly. It's got 1 valence electron. Well, if we've got 1 valence electron from a hydrogen, and we've got 2 hydrogens, that means we've got 1 times 2, that many valence electrons from a hydrogen. How many valence electrons does oxygen have? What group is it in? If you're not sure, just go over to your periodic table. Yeah, it's got 6, exactly. So we've got 2 plus 6, which gives us a total of 8 valence electrons. Okay, well, that's good. But what if we draw the Lewis structure of our hydrogen atom like this, and we'll draw the Lewis structure of another hydrogen atom like that. We'll draw the Lewis dot symbol of an oxygen atom like this. And if you're unsure, if you're really lost, and you're like, where did you get those from, Mr. Dion? Where are you coming up with that stuff? Well, it goes all the way back to this periodic table here. All I did was draw 2 hydrogens with a single dot and 1 oxygen surrounded by 6 dots. That's all I did. Okay, so I just drew the Lewis dot symbol. Well, what if we want to assemble them into a covalent compound, or a molecule that is made up of nonmetals, okay? Unlike an ionic compound that is made of a metal and a nonmetal, covalent compounds are made from nonmetals. Now, how would I combine these so that they all have essentially the benefit of enough electrons to have the electron configuration of a noble gas, if you will? Well, what if I took this hydrogen here and I brought it over here? I brought it next to this oxygen, right? Then if I connect my dots, okay, and I won't always do it this slowly, but if I connect these, son of a gun, if I connect these two dots right here, now the oxygen has the benefit of 1, 2, 3, 4, 5, 6, 7. Hey, it's pretty close to an octet, but it's not quite an octet. Hopefully you can see where I'm going with this. What if I took the other hydrogen and I moved it over here like this? Now, if I connected these two dots, now my oxygen has the benefit of what? 1, 2, 3, 4, 5, 6, 7, 8. So it has a complete octet. It's surrounded by 8 electrons, and my hydrogen is, each hydrogen is surrounded by 1, 2, and 1, 2 electrons. And that's all hydrogen needs. Hydrogen only ever forms one bond because it only has the 1s orbital available to it. And how many electrons can we put in an s orbital? 2. Okay, we spent enough time talking about that. So this would represent a Lewis structure of a water molecule. I'd like to try another one with you before we get moving here and getting into some more complex molecules. Let's try one more. What time is it? 5:47. So we've got what? 6 hours left. Okay. So let's say we tried a molecule like, let's try carbon dioxide, CO2. Well, how many valence electrons does carbon have? I'm going to go a little faster now. Carbon is in group 4A, so it's got 4 valence electrons. Oxygen is in group 6A, and I've got 2 oxygen, so that's a 12 plus 4, so that gives me 16 total valence electrons. Well, let's write down the Lewis dot symbol of my carbon, and I'll write down the Lewis dot symbol of my oxygen. Now, I'm going to go a little faster here, and if you're wondering, Mr. Tion, is there a stepwise procedure I could follow to draw, a Lewis structure? The answer is yes, and we're going to get to that in a second. I just want to show you quickly how you might, solve this kind of problem, how you might assemble these atoms into a covalent compound. Well, if I bring this oxygen over here next to this carbon, you can see that I could make a bond here, okay? And if I did the same thing with this oxygen, I bring it over here. Now, this carbon, we have, oops, where's my bond? There's my bond, like that. But now my carbon is only surrounded by 1, 2, 3, 4, 5, 6 electrons. So it doesn't have a complete octet. The oxygen has 1, 2, 3, 4, 5, 6, 7. So nobody's really happy here. So to make a long story short, the answer is this. I'm going to take this unpaired electron and this unpaired electron. I'm going to delete both of them. I'm going to take those 2 electrons and I'm going to make a single bond, right? Because every single bond has 2 electrons in it. I'm going to do the same thing on the other side, and now I'm going to have 2 double bonds. So this is a single bond, and now here we've got a double bond. Well, let's take a look at our carbon. Our carbon is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. Hey, it's happy. It's got a complete octet. Let's look at my oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So both oxygens have an octet as well. And that is kind of just an introduction to some strategy that you would employ to come up with a Lewis structure for a molecule. Now, you could even try nitrogen, N2, and when you draw the Lewis structure of nitrogen, you end up with a triple bond. And if you look at the structure of nitrogen that I've drawn here, you can see that both of them are surrounded by 1, 2, 3, 4, 5, 6, 7, 8. So they both have an octet. But I just wanted to introduce the concept of the single bond, the double bond, and the triple bond before we talk about the lengths of covalent bonds. So this is kind of a slide that I kind of did the treatment on the previous slide where we looked at water, carbon dioxide, and nitrogen. But anyhow, let's talk about the lengths of covalent bonds. I don't have a lot of things memorized in terms of exams that I've given over the years, but a number of years ago, one of the ACS final exams had a question in it. One of the very first questions on the exam in Chemistry 111 was about bond length. And it said, okay, well, if you've got a carbon-carbon single bond, double bond, and triple bond, how do they compare in terms of length? Which one's the longest? Which one's the shortest? Well, I can make this really quick for you. And that is, the more bonds that we have between atoms of the same kind, the shorter the bond length is. Now, I could go into quite a treatment on this and give you a whole dog and pony show about the reasons why. But in a nutshell, if you want to think, the simplest way I could describe it to you is this. In order for the atoms to share more and more electrons, they basically have to get closer and closer together in order for the orbitals to overlap to form those multiple bonds. So if we look at a carbon-carbon single bond, it's 154 picometers. We go to a double, it gets shorter. We go to a triple, it gets even shorter. If you don't believe me that this is a trend, well, let's look at what happens when you have a carbon and nitrogen single, double, or triple bond, and you see the same trend, that they get shorter and shorter. So this is something you've got to have in your hat with you when you step into the exam. I have it summarized right here that bond lengths, triple bond is going to be shorter than a double, which will be shorter than a single. And if you wondered about what is the definition of a bond length anyway, well, a bond length is nothing more than the distance between two nuclei in a molecule. So here we have a molecule of H2 or hydrogen and a molecule of hydrogen iodide. And you can see that the distance between the nuclei, they've kind of highlighted that for you, that is what the bond length is. Anyhow, there we go. So give me a thumbs up if you follow me on bond length. Triple bond shorter than double. Single bond is going to be the longest between elements of the same kind. Anybody with me on that? Why? All right. Branson, you're on top of it. Great. That's awesome. Okay. Well, with that in mind, I want to switch gears a little bit and give you an introduction to chapter 11. You're like, oh, Mr. Dion, come on. We're only in chapter 9. I don't want to be thinking about another chapter. Don't make my head hurt. Well, hold the phone. Hold the phone. I'm going to make this as simple as possible. Distill this into the simplest possible bits that you need to know. Let's take a look at an ionic compound and a covalent compound, right? Sodium chloride, just table salt, is an ionic compound because sodium is a metal. Chloride is a nonmetal, comes from chlorine. So this is an ionic compound. And then this next compound here, that's carbon tetrachloride. This is a covalent compound. So carbon is a nonmetal and chlorine is a nonmetal. Now, this is one of those slides that I could really go on, probably a 15-minute rant about it, and I'm going to try my best not to do that. But if you have a sample of solid sodium chloride, you can't tell me that you're all chemistry students. You can't tell me that you've never taken a piece of table salt, just one grain of salt, and held it in your hand and looked at it, and you've noticed that it's got that cubic shape. I know you have. Everybody does it, right? You look at the salt crystals. Well, what are the forces that are holding those ions together, right? We said it's an electrostatic force between a positive and a negative charge. It is strong, and that is why at room temperature, sodium chloride is going to be a solid, right? That's why it's a solid. Now, if we look at carbon tetrachloride, if we look at a molecule of carbon tetrachloride, well, carbon tetrachloride is a covalent compound, right? It's not, there's no cations and anions in here. There is like partial separation of charge, but that's neither here nor there at the moment. But what are the forces that are going to hold two molecules of carbon tetrachloride together? Okay, what are they? Well, the forces that are going to hold two molecules of carbon tetrachloride together, which is, carbon tetrachloride is actually a liquid. It's a clear and colorless liquid at room temperature. What holds those molecules together in the liquid phase are what are called intermolecular forces. Okay, but the intermolecular forces that hold molecules of carbon tetrachloride together can't be nearly as strong as the intermolecular forces that hold sodium chloride together. Because sodium chloride is being held by ions, right? Electrostatic force, whereas the covalent compound doesn't have the benefit of those ions. Now, in chapter 11, we'll go into a whole treatment of what those forces are. But for now, let's take a look at the melting points of sodium chloride and carbon tetrachloride. You got to heat up sodium chloride to 800 degrees Celsius before it's going to melt. Well, carbon tetrachloride melts at minus 23 degrees Celsius. That's really cold. So again, the whole concept here is that the forces that are going to hold the covalent compound together in a collection or a sample are going to be a lot weaker than the forces that hold ionic compounds together. All right. Anyhow, I would like you to take a look at this table in our textbook and spend some time looking at the information that's in our textbook with respect to this, because again, it's one of those things that I could go on and on about, and we're going to talk more about it in chapter 11. So I'm going to move on from there and get into what are called polar covalent bonds. Okay. So if you're, if you think that up to this point in the lecture, it's almost 6 o'clock, you think, oh man, this has been pretty content heavy, a lot of concepts here, lattice energy and this and Lewis structures and all this stuff. Okay, you can take a deep breath here, okay, because I think it slows down a little bit here. See if you can follow me on the idea of polar covalent bonds, because it's going to come up a lot in this chapter, and it's going to come up a lot in the next chapter. If I go to Costco with my daughter, like in the pre-COVID days, my daughter is 5 years old. Her and I would go to Costco, and sometimes we would buy a Costco pizza slice, okay? And we would share that pizza slice. Now, were we sharing it? Yes, absolutely. It was unequivocal sharing. However, who do you think is getting more of the pizza? Is it dad or a 5-year-old? Well, I'll just answer the question for you. It's me. It's probably going to get more of it. We are sharing it, right? We are definitely sharing the pizza. She's getting some, but I'm getting more of it. And we see the same kind of concept when we have a covalent bond between two elements that have a different propensity to pull electrons towards themselves. And that's the concept of electronegativity. Now, I haven't gotten into that yet, but a polar covalent bond, which is defined here, or sometimes we just call it a polar bond, is a covalent bond with greater electron density around one of the two atoms. Now, this is an electrostatic potential map of hydrogen fluoride. The red portion means that it's electron rich. So this part here, this is electron rich, where it's red, and where it's blue, that's electron poor. Okay? So you can clearly see that somebody took the time on their computer to show that there's a single bond there, right? There's a bond that shows the sharing of the two electrons, right? There's two electrons being shared in that bond. But if we look at the density of the electrons around the two atoms, you can see that most of the electron density is hanging out around the fluorine. Again, they're still sharing it, but the electrons spend more time in the vicinity of one atom over the other, and that's what we call a polar bond or a polar covalent bond. Now, if you're wondering, why would one atom pull electron density towards itself greater than the other atom? Well, that's based on a concept called electronegativity. Now, they say that there's only two absolutes in life, right? Death and taxes. I say there's three. There's death, taxes, and chemists love electronegativity. It's one of the favorite trends, periodic trends for students and maybe instructors alike, but I see students really like the concept of electronegativity. Well, what electronegativity is it's defined as the ability of an atom in a bond to attract electron density towards itself. Okay, so you have that hydrogen fluorine bond, and here's my Lewis structure of hydrogen fluoride. It's the ability of the fluorine to pull more electron density towards its dang self, okay? It's pulled towards itself like this, okay? Now you might be thinking, well, Mr. Dion, we covered that. That's electron affinity, right? It's, non-metals have a high electron affinity and they can become isoelectronic with a noble gas, right? Well, electron affinity, that's a quantifiable, electron affinity is quantifiable is what I should say. So it's measurable. Chlorine has the highest electron affinity in the periodic table, whereas electronegativity is a relative number. It's unitless. Okay, it has no unit. And if you were to actually do a Google search on electronegativity, there are not Avogadro's number, but there are several different scales of electronegativity. Now, I haven't looked at anything besides what's called the Pauling scale in years. But the scale that is most commonly used in an introductory chemistry class like this, or even in most advanced chemistry classes, would be what's called the Pauling scale. And it's named after Linus Pauling. So again, the electron affinity, I just want to pencil this in here for you. This is for an isolated atom, whereas electronegativity is relative, and this is for an atom in a bond. Okay, let me show you the trend of electronegatividity on the periodic table. So here are some electronegativities of common elements. Sometimes I'll see my students will have these fold out periodic tables, or sort of, everything I ever wanted to know about chemistry, kind of thing, fold outs. And if anybody has any of those, they're fantastic. They're wonderful. But oftentimes on those tables, you'll see electronegativity values listed to the 100th place, whereas everything here is just listed to the 10th place. So if we look at the electronegativities of the common elements, you see that number one, the king of the castle, is fluorine. Fluorine is the most electronegative element on the periodic table. Now, students usually don't have any problems memorizing that. They're like, yep, fluorine's got a value of 4. I'll keep that in my hat. Now, I don't expect you to memorize any electronegativity values. If you need one, I'll give it to you. However, it's kind of helpful to have a few of them under your hat. And if you can remember that in period 2, if you can remember that lithium starts with 1, then they just increase by 0.5. So you go from 1 to 1.5 for beryllium, to 2 for boron, to 2.5 for carbon, to 3, and 3.5 and 4, all the way over to fluorine. So that's kind of easy for the second period. Something else I want you to remember is that oxygen comes up a heck of a lot in general chemistry, right? Especially when we're talking about ionic compounds, because most ionic compounds that we're going to look at, I'll be frank, are either going to be group 1A, 2A cations, or an aluminum cation. And the anion will usually either be a halogen or oxygen, and sometimes sulfur and nitrogen, but most of the time it'll be a halogen and oxygen. So oxygen gets the silver medal. Oxygen is the second most electronegative element in the periodic table. So what's the trend? The trend is, as you saw, as we go across the period, like as we went across the second period, electronegativity increases. Now, I'm not going to go into the full treatment as to why that is at the moment, but I need you to know just the trend for right now, that as we go across the period, go from left to right, electronegativity increases, and the electronegativity decreases as we go down a group. And you can see that exemplified. Maybe we could just pick, I don't know, group 6A, right? If you go down from oxygen to sulfur to selenium to tellurium to polonium, you see that electronegativity decreases. You also notice that the least electronegative elements are way down here at the bottom of the barrel, right? You got cesium, francium, right? These are really elements that have a low electronegativity. Okay, so for now, all I need you to know is that the greater the electronegativity of an element, the greater ability it has to pull electron density towards itself in a bond. Okay, and fluorine is the king of the castle. It's got the greatest electronegativity. Oxygen takes the silver medal, and it increases going across a period, and it decreases going down a group. Okay, that's all I need you to know for now on. And I'm going to show you how to use these numbers later on in order for us to be able to qualify and partially quantify what is called a polar covalent bond, a covalent bond, or a nonpolar covalent bond, and an ionic bond. So we're going to kind of come full circle and get back to these concepts. All right. If you're the kind of person that has to see everything in a graph, and there's always somebody in a group that's like that, I worked in big pharma for a number of years, and there were some people you could show them, Avogadro's number of tables and everything. They'd be like, show it to me in a graph. I need to have everything in a graph, and there's nothing wrong with that. So if we take a look at the period, so here we have, this is the second period here. Oops. This is the second period here, third period, fourth period, fifth period, right? So on and so forth. Well, you see that generally speaking, as we go across a period, electronegativity increases. Yes, I know that there are some anomalies here. If we look at the transition metals here and here, however, I'm not going to focus in on all of the, every little exception to the rule. Okay, that's not what Chemistry 111 is about. If there's an exception that's important in Chemistry 111, believe me, I will let you know what it is. Well, before we take a short break, I want to talk to you about how we use electronegativity to describe what makes a covalent bond, a purely covalent bond, an ionic bond, and what makes that new kind of bond, that polar covalent bond, that bond where the electrons are shared but unequally shared. And here are some numbers that we can use. Now, the difference in electronegativity, which can be calculated as an absolute value, I call it delta En, which just means difference in electronegativity. I usually just take the highest electronegativity and I subtract the lower one to give me a positive number, but you could just use, an absolute value. But anyhow, if you have two elements bound together and you look at their electronegativities. If the difference in their electronegativities is less than 0.4, then you have a covalent bond, okay? And if you're like, well, Mr. Dion, if there's a difference of 0.3, that means that one of them has a greater electronegativity. That means it's got, there's more electron density. Is that really covalent? Is it really purely sharing? No, it's not going to be 100% equal sharing, but we qualify that as covalent. Okay, we say that anything below 0.4 counts as being covalent. If you're above 2, if you've got a difference of 2 between two elements in terms of their electronegativity, that counts as an ionic bond. And when you're somewhere in between, if you're between 0.4 and 2, that constitutes a polar covalent bond. So if we think about these differences, right? If we have a covalent bond, okay, and we talk about our delta En, or our difference in electronegativity, right? When it's less than 0.4, this is when we have a covalent bond and we have sharing of electrons. If it's between 0.4 and 2, this counts as a polar covalent bond. That's where we have a partial transfer of electrons. I'll talk more about that in a second, and I'll show you how we use the delta symbol to represent a partial transfer. I'll go into that in a little bit. And then again, if it's greater than 2, you, my friend, have an ionic bond. So something I'd like you to think about over our short break would be, take a look at these bonds, take a look at these molecules here. And two of them are molecules. One of them is an ionic compound. But anyhow, if you take a look at the bonds here, if you evaluate the electronegativity, or if you look up the electronegativity of the elements, I want you to figure out whether these bonds are ionic, polar covalent, or covalent. So we're going to take a 5-minute break. I need a drink of water really bad. It's very dry down here in my basement. So just give me 2 shakes of a lamb's tail. There we go.